Hello everyone and welcome to this new video where we will try and code a very simple positional encoding mechanism to see how it works under the hood. This is the third and the final video for the positional encoding series where we saw the theory or the intuition, and then we saw the math, and now the code. So the goal of the script is to understand and implement positional encoding, which is a very crucial mechanism in transformers that, as we've seen, injects the sequence order information into the input embeddings. So after embedding the sentence, for example, or a token, we will also inject the sequence order. We are going to implement this in two ways. First, we will use a loop-based approach just for the conceptual understanding, and then a more efficient vectorized NumPy approach for the actual usage. So what would we expect as output? We will see a small positional encoding matrix that confirms that both the naive and vectorized implementations produce identical results. And we will also see a heat map of standard sized positional encoding matrix. This visualization will reveal the distinct geometric wave pattern, the sine and cosine, that allows the model to distinguish positions across the different dimensions. So let's start. The first thing here is we will import the necessary math libraries, NumPy, and the plotting Matplotlib. It also said we will set up the hyperparameters for a simplified toy example to make the initial matrices easy to understand. For this one, sequence length, it is the number of tokens in the sequence. We will use 4 words in our example. The dimension of the embedding, this is the dimensionality of the embedding vector for each token. Let's say 4. The n is the like the scalar. It is usually 10,000, but we will use 100 for this small example. It is like the wavelength frequency. Okay, so we run this block of code, and now we will start with the naive or the for loop implementation. This function implements the standard positional encoding formula using the nested for loop. We will iterate through every position and dimension index to calculate the specific sign for even, cosine for odd values, indices values. This is simpler or more educational, but it is computationally slow. So we can see we will take the sequence length, the embedding dimensions, and the scaling factor. Okay, let's run this function now. We will execute it. We've set the default here 10,000 because we said it is the default, but we will give it 100 as we said. So we are here. Let's run it. We can see, as expected, like the first values, they change in big steps. For example, this one from plus 0.5 to minus 0.4 to minus almost 1, and here from 0.8, 0.9, 0.1 all the way to 0.1. But in later these values, the third and the fourth, we can see a much slower rate of change. from 01 to 02, and here from 1 to 098 to 096. This is what we talked about in the previous math video. Okay, now we will do the more advanced or vectorized approach. This would like we will get the same output as this one. We will then verify with the assert function. But we will use the NumPy vectorization and broadcasting by implementing loops. This implementation is significantly faster and is the standard way to implement layers in deep learning. Again, we will take the same inputs or parameters. So how do we do that? The first thing is we create the matrix and all the values. We create the positions vector. So the shape becomes the sequence length and then 1, the vector. And create the geometric progression of the denominator. We add, and now we define the term, this one, this is from the formula. We do the calculation of the denominator and then the argument. And then we apply the sign for even columns and cosine for the odd ones using this. So here we start from 0 and then add 2, like go with 2 steps, and then here start from 1 and then 2, so we will only go to odd columns. So it's pretty much the same, but it's just faster using like this trick, this one here. Okay, let's run this, and now we should get, yes, success. So what we got here is the same as what we got here. Okay, now let's see the matrix that we talked about, the positional encoding matrix. We will plot it as a heat map. This will show us how the sine and cosine wavelengths stretch out as the dimension index increases. As we can see, the right part and the left part. So it would create a unique pattern for every position. So this position here, it's different. You can see it visually, it's different from this line here, etc., etc. Yeah, and we don't have anything to say here. It's just the positional encoding matrix. It's pretty simple. And now I've added this function, but we didn't use it. This is a function that shows how to apply the generated positional encoding matrix to the real-world embeddings. So we said we take the embedding and then we add the positional embedding. After creating the positional encoding, we will add it to the embedding that we have. This is the input shape. It should be batch size, sequence length, and the dimensions of the model. So yeah, we usually multiply embeddings by the square root of the D model, and then this is just to scale them, and then we add the positional encoding that we have. So yeah, that's it. This is a pretty simple and straightforward video. We know that in real life there are already some pre-trained models that are even open source. So this was just to understand the math. So thank you for watching. Please like and subscribe if you liked the video.